All right. So thank you so much for coming to, oh, thanks, Sam. Thank you so much for coming to this week's of GOCC. Today we have Sam talking to us about supermajor index and Thrall's problem. But before we begin, let's go over our community guidelines. We are all learning, everyone has something to contribute, and no one has all the answers. So with that, take it away, Sam.
Awesome. Yeah, thank you for the introduction, Miski, and thanks to all the organizers for having me and putting this wonderful colloquium on every week. So yeah, let's I maybe want to start by describing a couple words in the title. So Thrall's problem is this old problem dating back to 1942 in representation theory. It still remains open in general, and the content of this talk will not consist in solving more special cases, but rather describing a certain generalization of Thrall's problem that uses this fun new combinatorial statistic called the supermajor index. Okay, so there we go. Just to start, I said this is a problem in representation theory. Let's talk about how we do representation theory as combinatorialists. To start, the group we'll be working with pretty much the entire time is the general linear group, GLN. So we can think of this, perhaps after fixing a basis, as the group of invertible n by n matrices. And we're going to say that a GLN module is just some complex vector space E on which the general linear group acts. And one very important construction, especially I think for combinatorialists, is this notion of the character of a module. And the idea is we look at how the diagonal matrices act. When we restrict the action of GLN just to the diagonal matrices, look at how this acts on our vector space. And from the trace of this action, we associate a certain polynomial called the character and denoted with a lowercase ch. So just as a quick example of like how we get the character out of a module, one pretty nice straightforward GL3 module is just the three-dimensional complex vector space. GL acts on this by matrix multiplication, so that means that C3 is a GL3 module. Under this action, if we look at the action of the diagonal matrices, the set of unit vectors form an eigenbasis for the action of the diagonal matrices. So for instance, if I just consider a diagonal matrix in the variables x1, x2, x3, I act on the first standard basis vector. That's an eigenvector with eigenvalue x1, or just whatever the 1, 1 entry in my diagonal matrix is. Similarly, I act on the second standard basis vector. That's also an eigenvector with eigenvalue x2. Third standard basis vector is an eigenvector with eigenvalue x3. So to get the character of this representation or of this module, I just look at the trace of this action. I sum up all my eigenvalues, and that's this polynomial here. I just get x1 plus x2 plus x3. I should also, I don't think I mentioned at the beginning, please feel free to stop me with questions at any point if something's unclear. All right. So one really nice fact in GLN representation theory is that the irreducible GLN modules are just indexed by integer partitions. So these weakly decreasing sequences of integers with at most capital N non-zero parts. And if I go and compute the character of these irreducible modules, I get the Schur symmetric polynomials, which is a particularly nice combinatorial family of polynomials. So for those that haven't seen Schur polynomials before, I think I'm just going to again introduce them through an example. So the idea with the Schur polynomials is they're indexed by integer partitions. For instance, if I take the integer partition 2, 1, 0, I'll depict that as an array of boxes with 2 boxes in the first row, 1 box in the second row, 0 boxes in the third. And then I consider all the ways I can put numbers into these boxes in such a way that the numbers weakly increase along rows. So I'm allowed repeats in the rows and strictly increase along columns. So I'm not allowed to have 2 1s in the first column, for instance. So I consider all the possible ways I can do that with the numbers 1, 2, and 3. So yeah, these are called semi-standard Young tableaux. These weakly increasing along rows, strictly increasing along columns. Each semi-standard Young tableau, I can associate a monomial to it by just looking at how many 1s appear, I raise x1 to that power, how many 2s appear, raise x2 to that power, so on and so forth. So like this first semi-standard tableau, for instance, it gives the monomial x1 squared x2, whereas maybe just picking out one like further down the line, here I have this guy here, I have a 1 and 2 3s. That gives me the monomial x1, x3 squared. So I consider all the possible ways to do this, sum up the corresponding monomials. This gives me what's called the Schur symmetric polynomial associated to that partition shape. And although it's really not obvious from the definition, the Schur polynomials are symmetric in the sense that if I exchange 2 variable indices, the overall expression isn't changed. So for instance, like if I switch x1 and x2, this first monomial would become x1, x2 squared. That's accounted for over here. And likewise, this one would become x1 squared x2. Things shuffle around a little bit, but the overall polynomial stays the same. So the Schur polynomials are symmetric, and in fact, as if I let mu range over all integer partitions, the set of Schur polynomials forms a basis for the space of all symmetric polynomials in the variables x1 through x capital N. So we see that the symmetric polynomials take on a particular importance in many different areas of combinatorics, but in particular here in GL representation theory. Okay, and one final nice fact to hit you with. So I made this claim that the irreducible GLN modules are indexed by integer partitions. Didn't really say what irreducible is, but the idea, as the name kind of suggests, is that if I take any arbitrary GLN module, I can decompose it uniquely into irreducible modules. So the irreducible sort of form like the building blocks of my GLN representation theory. So what this means is, right, I have a direct sum decomposition of some number of copies of each E mu. And sorry, this should be a, oh, whoops. Sorry, the subscripts here should all be mu's, I apologize. But I have some direct sum over the irreducibles, some number of copies of each irreducible, and that uniquely determines any given module up to isomorphism. And so sort of by this first nice fact, if I want to find the irreducible decomposition of a GLN module, this is equivalent to expanding its character in the basis of Schur functions, right? Since the character of the irreducibles are the Schur functions are linearly independent. Finding the character of the module is equivalent to determining the irreducible decomposition. So the next I'm going to introduce like a particular GLN module that was originally considered by Thrall. he, asked the question, like, what is this irreducible decomposition? The viewpoint we're going to take on this is through the character theory. So instead of like explicitly finding the irreducible decomposition, I'm going to be saying, okay, what's the character of this? How does the character expand into Schur functions? Okay, any questions on the background before I continue? Okay. So this module I'm going to define comes from an algebraic object called the free Lie algebra. And the way it's constructed is as follows. Okay, so start with capital N dimensional complex vector space, and let's fix a basis for it. So Z1 through Zn. From the vector space, I can form what's called the tensor algebra of V. So this is just the space of all, spanned by all like tensors of all orders of V. But what we can think of it as is like once we fix a basis, the tensor algebra is just spanned by all possible words in the alphabet Z1 through Zn. And it comes equipped with a natural grading, where each graded piece consists of all the words in this alphabet that have length exactly n. So that's what this V to the O times n represents. So inside the tensor algebra, I can form the free Lie algebra. The way I do this is I just take my the basis I fixed before, and take the least subalgebra of the tensor algebra that's generated by this basis. So what this means, again, like maybe hopefully an example will paint a better picture. If capital N equals 3, I fix a basis for my vector space with 3 elements. I can form the tensor algebra. And then sitting inside of the tensor algebra is this, what's called the free Lie algebra, where I just construct it by taking all possible iterated Lie brackets of my 3 basis elements, with this convention that since I'm in the tensor algebra, the Lie bracket of 2 basis elements will just be this commutator, Zi tensor Zj minus Zj tensor Zi. And so just as the tensor algebra has a grading by like the length of the word, so does the free Lie algebra. And the idea is these graded pieces are like spanned by the iterated bracketings with exactly n basis elements in them. So for instance, the first graded piece, L sub 1, is just spanned by my original 3 basis elements. No way I can get like a bracketing with just 1 element other than that. So that's just isomorphic to my original space. The second graded piece is spanned by all possible bracketings of 2 of my basis elements. So Z1 bracket Z2, Z1 Z3, or Z2 Z3. And again, in the tensor algebra, I'm like identifying these brackets with, for instance, Z1 bracket Z2 is Z1 tensor Z2 minus Z2 tensor Z1, so on and so forth. Then the third graded piece will consist of all ways I can put brackets around 3 pairs of 3 elements. This gets like a little messy to write out fully, but hopefully this paints a somewhat clear picture. Okay, and now with the definition of the free Lie algebra in hand, we can move to Thrall's problem. This slide is very notation heavy. I wanted to include it for completeness and for anyone that would be interested, but this won't be super important to what we're talking about going forward. I'll just maybe put up the upshot. Is that Right, so I can consider how the general linear group acts on my original vector space V. This extends to an action on the tensor algebra of V, which is then inherited by the free Lie algebra. So the free Lie algebra is itself a general linear group module. And then some results from Lie theory, I can use the PBW theorem to get a certain decomposition of the tensor algebra as a general linear group module. And this decomposition involves the free Lie algebra in some way. So okay, if none of these symbols make sense, but upshot is I can form this interesting tensor algebra decomposition using the graded pieces of the free Lie algebra. And so Thrall, back in 1942, originally found this nice decomposition and asked the kind of natural question. We have this nice decomposition. So each of these pieces, which are indexed by integer partitions, we can ask for their irreducible decompositions as well. So again, just as a reminder, finding the irreducible decompositions of these higher Lie modules by taking characters is equivalent to expressing the character of the higher Lie module in the basis of Schur functions. Okay. So I just want to do a brief little literature review, right? Since this problem has been open for about 80 years, just detail a very, very small sliver of the work that's been done on Thrall's problem. So first, as a shorthand going forward, instead of writing out my full set of variables x1 through xn, when we pass the characters, the dimension or the number of variables doesn't matter all that much. So I'm just going to use a boldface x to denote my variable set. In particular, in the literature review here. So the first, I think, major result concerning the free Lie algebra was by Brandt, who was actually one of Thrall's students in 1944. So she determined the character of the nth graded piece of the free Lie algebra in the basis of power sum symmetric functions. So this doesn't quite tell us what the irreducible decomposition would be, but it's certainly a step in the right direction. And it's this kind of weird looking expression. It uses the Mobius function from number theory, the divisor function. It was kind of, I think, it was bizarre for me, at least the first time I saw it. Next up, in 1950, Marshall Hall introduced the Hall set, which determined a basis for the free Lie algebra as a vector space. And I'm not really going to talk about the Hall set at all. But I just wanted to talk about this interesting historical note. So the Hall set, Marshall Hall actually named it the Hall set himself, but claimed it was named after Philip Hall, who came about 15 years prior. And not to speculate past judgment or anything, but pretty cool way to name something after yourself. Okay, anyway, after, I think the next development to talk about is in 1974, Kiewicz described the Schur-Weil dual of the nth graded piece, which is this, I guess I'm not really talking about Schur-Weil duality, but it's this essentially the mirror of the nth graded piece as a symmetric group module and instead of a GL module. And it was Kiewicz' work that allowed Kraskevich and Weyman later in 1985 to finally describe the Schur expansion of the nth graded piece of the free algebra. So this is like the single row case of Thrall's problem, where the indexing partition is a row. And oops. My bad. Okay, yes. So this final result of Kraskevich and Weyman is the one I want to hone in on. In particular, like I mentioned at the outset, we're going to be considering a certain generalization of Thrall's problem. We're not going to be solving any more cases in the classical setting, but rather generalizing it to a different setting and sort of lifting Kraskevich and Weyman's result to this case. I'll also point out we did also generalize Brandt's formula and Klyachko's result to this setting. I'm happy to talk about that at the end, but it's not as interesting or enlightening, I guess, in this case. So right, this single row version of Thrall's problem is going to be our essentially the main focus of the rest of the talk. And so the way this, or the expression we get for the character of the nth graded piece has to do with the major index statistic. So the major index statistic is defined on a standard Young tableau, and it uses the descent set. So I have an example. Yep, may as well just put that up. So the set of standard Young tableau of a partition shape is just the set of all fillings of that partition shape. So like down here, for instance, I have the partition 3, 2. I consider all possible ways to fill that partition shape with the numbers 1 through n is in this case 5, such that the numbers increase along rows and down columns. And then to enter any standard Young tableau, I can associate the descent set. So this just consists of all the indices I, or the entries I, such that I plus 1 appears in a lower row of my standard tableau than I. So the way to think about descents is if you're kind of like tracing the numbers 1 through n with your mouse, we have a descent whenever I have to go down. So 1, 2, 3 down. So 3 is a descent across. Over here, I go 1, 2 down. So 2 is a descent. 3, 4 down. 4 is a descent. So on and so forth. And now the major index of a standard tableau is just the sum of all of the descents. So for instance, in this second tableau here, my descents were at my entries 2 and 4. So the major index is just 2 plus 4 is 6. And right, I can play this same sort of game, get the descent set for each standard tableau, associate the major index. Okay, so now to Kraskevich and Weyman's result. They found that, okay, so right, as I mentioned, they found the expansion of the character of the nth graded piece of the free Lie algebra in the basis of Schur functions as follows. The coefficient on the Schur function indexed by mu is the number of standard tableau shape mu whose major index is congruent to 1 mod n. Kind of like kind of strange. Just as a an example of one of these computations, the set of standard tableau here, I went through and computed all the matches on the last slide, found that, so I guess on the left are the matches, and then I want to take all these matches mod 5. So mod size of my partition, I find that there's exactly one standard tableau of shape 3-2, whose major index is congruent to 1 mod 5. And that tells me that the multiplicity of the irreducible module indexed by the partition 3-2 in this 5th graded piece is just 1. And if time allows later, I'll say a little more about why this, or at least try to hint at like how this like weird modularity comes in, because pretty weird. Oh yeah, so I maybe remark, this is right, these like the graded pieces of the free Lie algebra sort of correspond to the single row case of Thrall's problem, where the indexing partition is just one row. And outside of this, this is in a sense like the only interesting case of Thrall's problem that's known. The other known case is when the indexing partition is a 2-column shape. But this actually follows from one of the only known platistic identities, which can be found in, I think, Macdonald's book on symmetric functions. But right, outside of this, the single row case is kind of state of the art. Okay, so now I want to introduce the generalization of Thrall's problem that we considered. So I guess the guiding heuristic is that instead of starting with a regular vector space V, we're going to start with a super vector space, so or a Z2 graded vector space, which I'll denote by bold V. This is just like a vector space that has an even and an odd part, and which I'll denote by V sub 0 and V sub 1, and just try to play the same game that Thrall originally played. This will mostly just consist of adding the prefix super where necessary, and most of the time things just nicely work out. Okay, so just as before, I have my super vector space. I can form its tensor algebra. Again, this consists of words that are spanned by words in my vector space. It has a Z2 grading, which won't be super important to us, but it does also have a bigrading. So this T to the NM consists of all of the words with exactly N letters from my even component and exactly M letters from my odd component. And then inside the tensor algebra, I can form the free Lie superalgebra, where just as before, if I fix bases for my even and odd components of my super vector space, I just like take all possible brackets and iterated brackets on that basis, except now the way I define my bracket is up to this like extra little sign of a -1 to the component of x times component of y. But the way it's constructed is essentially like analogous to the way it was before. And just as before, we have, well, sort of as before. Before the free Lie algebra has a single grading. Here, the free Lie superalgebra has a bigrading, where this n-mth component, like in the tensor superalgebra, consists of bracketings with exactly n letters from the even component of my vector space and m letters from the odd component. All right. So now let's talk about super Thrall's problem. Again, as a pretty notation-heavy slide, including for completeness. I don't think I'm going to say much about this, but right, the upshot is that just as in the classical case, I can decompose the tensor superalgebra into submodules that involve the bigraded pieces of the Freely superalgebra. And in this case, the indexing set is no longer partitions, but non-negative integer valued matrices with finite support. And so for each such matrix, I can I define this particular module, and then as A ranges over all possible matrices, I get a decomposition of the tensor superalgebra. So this again, allows us to, or we can kind of naively state a super version of Thrall's problem. In particular, if the dimensions of my even and odd components of my vector space agree, then I can essentially consider both the tensor algebra and the Freely superalgebra as just a regular old GLN module. So it's sort of the natural extension is to ask what's the irreducible GL decomposition of these what we call super higher Lie modules. But just like in the classical case, this appears intractable. Maybe we've even made it more intractable. But what we can ask is, well, the single row case in the classical setting was known. Maybe we can lift that result to the super setting. And that's exactly what we want to do. So right in the classical case, Kraskevich and Weyman found the character of the singly graded pieces of the Freely algebra. Now what we want to do is find the character of these bigraded pieces of the Freely superalgebra. Okay, and so to do this, we're going to just define sort of an appropriate generalization of the major index statistic. Recall that was the what Kraskevich and Weyman used in the classical case. But what we're going to do is define it on what are called standard super tableaux. So the idea behind standard super tableau, so for a partition shape mu, these will be denoted by SYT plus minus. The idea is I just start with a regular old standard Young tableau, like you see on the left here. But then additionally, I designate some of the entries in the standard tableau to be negative. So this is essentially the data of a standard tableau and a subset of the numbers 1 through n. I can also kind of write it in this nice compact form as by denoting the entries in S with red overlines. Okay, so that's a standard super tableau. And we define or sort of lift the notion of the descent set to this case. So it's kind of maybe a lot to read, but the super descent set of a standard tableau will be the set of all regular descents in the original standard tableau, such that the entry I plus 1 is not negative, or plus the set of all non-descents from my original standard tableau that are in fact negative. And then I can define the super major index as just the sum over all super descents. So let's just go through and compute the super descent set really quick. You can check in our original standard tableau over here, the descent set is 1, 4, 6. So now I go through and say, okay, well, 1 is a regular descent of my standard tableau, but 2 is a negative entry. So this is not an element of this first set up here. I have a descent, but I as a descent, but I plus 1 is in fact negative. So 1 is not included in my super descent set. Meanwhile, 2, for instance, is included in the super descent set because it's not an original descent, but it is negative. So it falls into this, this second family up here. And the same goes for 3. It's not a descent of the standard tableau, but it is a negative entry. And finally, 4 is a descent of the original standard tableau, but 5, 4 is a descent of the original standard tableau, and 5 is not negative. So we do include 4 in the super descent set. And then we go through and check that that's all of them. And finally, we just my apologies. This should read S-Maj, super Maj. Is just the sum of all the super descents. So 2 plus 3 plus 4 gives us 9. All right. So yeah, here's the statement of our definition again. And so our theorem is that the character of the n-mth bigraded piece of the Freely superalgebra is given as follows. So the coefficient of the Schur function S mu is just the number of standard super tableau with exactly so standard super tableau of shape mu with exactly m negative entries and whose super major index is congruent to 1 mod n plus m. So notice if we, or maybe I should point out, if we set m equal to 0 here, that means I have no negative entries on my standard super tableau or just regular standard tableau, and I just recover Kiewicz and Weyman's result. Okay. So I just want to say a few words about how we proved this, because it was basically just a lot of generating function magic. So first, in the classical case, there are these nice identities for what's called the principal specialization of the Schur function. So the idea is I take some indeterminate q and just plug in successive powers of q for my variables in the Schur function. And there are these two really nice expressions for what I end up with that can be both found, for instance, in like EC2 by Stanley. The first is this hook content formula. So it's like a product over the boxes in my integer partition of q to the row of that box over 1 minus q to the hook length of that box. So there's kind of like how many cells are right plus how many cells are below that particular cell. And so this gives me the first nice identity for the principal specialization. But then there's also this nice expression involving the major index statistic, displayed on the right here. In the super setting, there's this notion of a supersymmetric Schur function, which I won't define explicitly, but we can think of it as it's like a two-variable generalization of the Schur function. So in the variables x and y. We can consider like a similar specialization where the x variables specialize in the same way as above, and the y variables, I just do the same thing but slap a t on the front of everything. So this first equality from the classical case was generalized by Macdonald in a really nice way. We just kind of pick up this extra factor of t times q to the column minus 1. And so what we did was essentially filled in this second equality in the super case. So we showed that the same specialization of the super Schur function can be written as a sum over superstandard tableau using our new super major index statistic, plus a factor of t. Okay, and this is really like the key ingredient in our proof of this theorem. So just a very like hand wavy sketch of the proof. The idea is that so the expression on the right hand side of the theorem over here can be obtained from this expression on the left hand side of the proof. If I just extract all the coefficients of t to the m and q to the 1 mod n plus m. All right, but by I guess by the theorem above, we can rewrite this left-hand sum as a sum of regular Schur function times specialization of super Schur function. And then there's a nice like supersymmetric generalization of the Cauchy identity in the classical case, which kind of describes this equality between products of Schur functions and power sum symmetric functions. And again, there's this like supersymmetric generalization of power sums that I won't define, but I will say the coefficients we want are much easier to extract from this expression. And then to conclude, well, so we get this expression in the power sum basis. It's easier to explicitly compute the character of the nth graded piece in the power sum basis, and we just show that the expression we get from here is the same as the expression we got for the from the original character computation. All right. So I just want to briefly conclude by talking a little bit about why MAG, the major index statistic, shows up in all of this. And it really comes from the coinvariant algebra. So the coinvariant algebra is, we take the, define it by taking the full polynomial ring in n variables and quotienting out by the ring of symmetric polynomials that have no constant term. So the co-invariant, because it's what we're left with is everything that's not invariant under the action of like variable permutation. And as such, the coinvariant algebra is a symmetric group module. And so just like for GLN modules, there's an essentially analogous way of defining the character of a symmetric group module using symmetric functions. So this is what's called the graded Frobenius character. We say graded because the coinvariant algebra is itself graded. So this contains a little bit more information in that, like, not only does it tell us how the module decomposes into irreducibles, it tells us how each graded piece decomposes into irreducibles, and that's tracked by like the power on this extra coefficient q. All right, but so the graded Frobenius character of the coinvariant algebra is given as this sum over Schur functions weighted by the major index statistic. And so what Kreskevich and Weyman actually did to prove their result was they showed that the Schur-Weil dual of this nth graded piece, which is again like kind of the symmetric group mirror of this GLN module. But this Schur-Weil dual is actually isomorphic to the subalgebra of the graded pieces whose exponent is congruent to 1 mod n. This subalgebra of the coinvariant algebra is isomorphic to the Schur-Weil dual of the nth graded piece. And then by taking right, if I take the coefficients of 1 mod n up here, I get precisely that result. So that's, just to say a little bit about how MAD shows up and this weird congruence mod n thing. But I also wanted to mention it because we were actually recently able to provide a similar interpretation in this super case. So what I want to do is take, sorry for the changing the index name, but hopefully you'll forgive me. Take the regular co-invariant algebra in k variables, tensor it with the polynomial ring in k anti-commuting variables. So I guess this is essentially like the exterior algebra in k anti-commuting variables. And I'll define r tilde of k to be this tensor product. Given the specialization theorem we had before, it's actually not too hard to show that the bigraded Frobenius character of this r tilde is given in terms of our super major index statistic. And so in particular, if I take the bigraded pieces whose like congruent to 1 mod n plus m in the first component, m in the second component, this subalgebra is isomorphic to the Schur dual of our bigraded pieces as S n plus m modules. So yeah, that's, I think, all I wanted to say. Thank you for listening.
Oh, any questions for Sam? Feel free to unmute yourself and just ask or put stuff in the chat.
I have a question.
Yeah.
Hi. Very nice talk. I was wondering, do you know anything about idempotence?
Yeah, that's a great question, and the answer is no. We haven't given any thought to that yet. It's yeah, definitely future directions, but don't have anything anything to say about them, unfortunately.
Sliotka's idempotent, right? Using the MAD.
Right. Yeah, there's that in the. I think that in the Reutenauer idempotent was the other. But one might not as be as. But
yeah, there are a few of them.
Yeah, yeah. But yeah, nothing to say about them, unfortunately.
Thank you.
Yeah.
Okay, let's thank Sam again, and I will stop the recording.
Thank you all.